Dr. Jorma Rissanen was born and raised in Finland, but soon after having made his PhD, he left for the big world out there. He has worked in many fields: numerical analysis, systems theory, information theory, and statistics. Today, he speaks on complexity and information in contingency tables. It is a great pleasure for me, on a conference in Finland, to hand over the floor to Dr. Jorma Rissanen.
Before getting to the main topic of my talk, namely the contingency tables, about which I will say quite little, I'd like to describe a couple of ideas. One is the notion of stochastic complexity, and the other one is the associated global maximum likelihood principle. So statistics begins with the observed data, X or X superindex N. And intuitively speaking, and even otherwise, what we want to do is we try to learn the constraints in the data, what makes it tick. And the way this is done is that we introduce model classes. These classes serve as theories or language in which we express these properties that we would like to learn about the data. Specifically, I'm interested here in two cases, two kinds of model classes. One is that we have the likelihood function, and then we also have a distribution on the parameters, the prior. The second case is like the first, except that there is no prior. Intuitively speaking, by stochastic complexity of the data X, I mean the fewest number of binary digits that it takes to describe or encode this data set when we try to take advantage of the models in the model class. And what's the rationale behind it? It is that essentially all descriptions that we cook up are redundant. And if we spot any constraint, we will be able to remove this redundancy, have a more compact description. So this way, if we spot and remove all the redundancies that we can in terms of the model, chosen model class, then we will wind up with the very shortest code length. Now, technically, the way these codes are constructed, actually we don't need to construct them, but we can think about the constructs. They have the important property that if we raise 2 to the negative power of this length, the number of bits, the result defines automatically a distribution. So there is an important normalization involved. And hence, since the stochastic complexity is the shortest code length, it necessarily means that we have been able to define the very largest probability, or assign the very largest probability to the observed data sequence. So in this, and if it moreover happens that we would find a model in that class that sort of corresponds to the shortest code length, then this model would represent the most likely explanation of data. So this is the broad rationale behind the coding. So we are not fundamentally interested in coding, but as you see, it is it is really something extremely basic. In fact, a case can be made that it's more basic than probabilities. So far all is good and well. However, we still have a problem. How do we get this shortest code length? Now, we know from Shannon's work that if there is a single distribution, then it is possible to construct a code such that its length is about the negative logarithm of this distribution. And moreover, such a code would be of that length. You can't beat that by any other way of doing the coding. Now, our situation is a little more complex because we have a whole class of distributions. So how do we get to this code length? Well, I'm going to flatly define it in a certain way, and then argue afterwards that the definition is justified. So the case one, where we prior, the task is a lot simpler. All we need to do is to work out the marginal distribution, take its negative logarithm. But if we don't have a prior, then we don't have the marginal either. And we have to go in a little more complex way. And here is how. We just first begin with by integrating out the parameters with the likelihood alone, unless this data sequence is very, very short because of the peaked property of the likelihood function. So let's assume that it exists for all t larger than or equal to 1. Then we can define a distribution on the parameters simply as the likelihood function normalized accordingly. And we can define a conditional density function by simply using this so constructed distribution and the corresponding condition which we have in the family. And the result turns out to be the ratio of two of those adjacent k values. And then multiply all those together and take its negative logarithm, and the result is going to be the negative logarithm of the largest of these k functions plus logarithm of c, where c turns out to be the ratio of the smallest of these k functions, and something, a new density function we can pick any way we like. So suddenly we have a chance, if you or liability, depending on your viewpoint, to represent your prior knowledge not as a density function on the parameters, but as a density function on the first piece of data. And if you can make this construct, that is, if you can work out that integral, we have that's one possibility. And it so happens that notice that in the parameter space. So we don't have the difficulty of not having a uniform distribution. And nevertheless, then these two complexities would equal if the prior here would be the uniform distribution. So to summarize the situation, we have defined the stochastic complexity of the data relative to a model class. Now, one can prove theorems to the effect that for long strings, you can't beat this by any coding. Even for, let's say, medium size samples, these lengths are extremely hard to beat, but they can be beaten. But you would have to be very, very clever in constructing the code. So that in that sense, fairly well justified as representing the shortest code length relative to the classes or models. And we also saw that this traditional prior is by no means the only way to represent prior knowledge. In fact, it's about the least important way. Because really the prior knowledge is used to pick these model classes. A different story altogether. Suppose then that we have let's take here, a finite set of these model classes in the contingency tables. Then we can simply find out that class which minimizes the. We will have a global maximum likelihood because raised to the power of minimum complexity will be under the assumed condition. And it is somehow related to Bayesian approaches. However, there are going to be fundamental differences, and to clarify those. As far as the central notion of Bayesian philosophy, which of course is a mushy and wide concept, but is the transformation from distribution affected by the data. While in stochastic complexity, the central notion is this distribution P of x, which sometimes agrees with that marginal distribution. Let us think of that will maximize the posterior distribution as that. Why not do that and skip the whole story with stochastic complexity? Let's see what happens. So we minimize the negative logarithm of the posterior. That's the same thing as difference between two terms. One is, let me call it MDL of data X given the model class, and the second term is the stochastic complexity. Now, terms have something that is responsive to the complexity of the model, namely to the number of parameters. Nothing but the important term cancels. And does not be impossible to learn anything about anything different numbers of parameters. And that of course is one of the fundamental problems in all of statistics. Everything else is semi-trivial. Is a basic approach. Not even where we have higher distribution. Only in the other case. So let me finally get to the contingency tables. So the of the whose entries are non-negative integers. Sort of occurrences. There's an underlying data sequence. And polynomials, and they express various rather complicated the variables or the dimensions in that. And this idea of ours is the for which the stochastic complexity. In fact, you compute it for all. The winner would then best incorporate all the independent study with that set of model classes. And it also assigns the highest probability and so on and so forth. Now the important thing about irrelevant. No one asks for the investigator's opinion what are the constraints in the table. Offend someone, but on the other hand, it makes the whole approach what I see. The traditional approach is not scientific. You get whatever you like. So and perhaps entertaining value depending on what kind of demands you have. Let me show a numerical example from there are 42 children feeding babies, and the question is the of hypothesis products of the margins, marginal probability, and we would have two free parameters, complexity, and it's given that formula. The hypothesis states that the cell probabilities are have three. So hence, and again, computed from such a formula. Because if we just look at the difference, we'll get that formula and the numerical, which means that dependence. Now this turns out to be a borderline case. The classical either depending on how you pick. Now in fact this could also be interpreted as some sort of testing. Is like a test statistic, it's positive. And like math. That this test would be uniformly most powerful, unbiased with this natural. Because this stochastic complexity based test, if you like, is always either uniformly most one of the, if the null hypothesis is simple, and of course if those. Now in this case, it's simple and still we got the uniformly most powerful unbiased test. Supposed to incorporate all the information there is in the data and that can be captured by those models, then evidently the test ought to be. So the result is not me at all. Contingency tables is somewhat more complex but similar. There I just picked them, I tagged one, which so at all. It just depends on the number of the total number of the sum of the entries. no free or saturated class, and M1 is the independent variables familiar between. Stochastic complexity is quite straightforward. All classes except the second, which is the no second order, I guess, level interaction. Modification, even that class can be handled. And these examples. Examples, and the bottom model has none. And here are the stochastic complexity. And the winner turns out to be in the they are. Now this bottom model that parameter reference ground model, and it will give the complexity. Hence we can interpret them as amount of information extract from the data. So that explains first of the paper. Now, curious that the saturated model wins. The traditional analysis would give the degree interaction model the best score, but as I say, even that the ordinary test nothing but roughly like this, that you assume in turn is data generating machinery, and then the test statistic would be the Kullback distance between that, and then you would accept the model. But I never fully understood the reasoning behind it, but that's the way it roughly goes. So you accept hypothesis is Kullback distance is small. The number of the saturated model to itself is smallest of them all because it's 0. Looking at the smallest distance. So somehow among these many small ones, judgment that it's that. That's the way I understand the ordinary hypothesis. Time.